we'll find out the electric field just outside the charged conductor. So we have a charged conductor which contains a positive charge. The whole charge is situated on the surface of the conductor because the conductor cannot have any charge inside itself. The whole charge comes on the surface of the conductor. So we will find out the electric field outside the conductor. Let us take a point P at which the electric field is to be calculated. So what we do? We draw a Gaussian surface. The Gaussian surface that will contain the point P. The Gaussian surface is a cylinder whose one parallel surface is outside the charged conductor. It contains point P. And the other surface, parallel surface, is inside the charged conductor. So you can see I have drawn only one surface outside the conductor. The electric field is normal to the charge, to the surface E and dA. The other part, the other surface, parallel surface is inside the conductor. So we have electric flux. Flux is equal to E dot dA. Here the electric field and the area vector, both are parallel to each other. So cos 0, theta equal to 0, it is cos 0. Phi E, surface integration E dA cos 0. Cos 0 value is 1. So surface integration of E dA. Now E is constant. We have surface integration of dA. Then total area of the parallel surface is A. This area, circle of plate, is A. So flux passing through this area is EA. Now we know from Gauss's theorem phi is equal to Q upon epsilon naught. The whole charge distributed over the charged conductor is sigma. That is the surface charge density. So Q is equal to sigma A. So electric flux is equal to sigma A upon epsilon naught. We compare these two equations, equation number 1 and equation number 2. Here EA equal to sigma A upon epsilon naught. A and A cancelled out. Electric field to a charged conductor is given by sigma upon epsilon naught. We will find out the electric field due to a thin charged spherical shell. What is a shell? It's a hollow sphere. So we will find out the electric field at different points of the shell. That is, 1 on the surface of the shell, 2nd outside the shell, 3rd inside the shell. So I have drawn a spherical shell here. This is the shell. Closed line is the shell. The broken lines, this is inside the shell. We have a point P dash inside the shell. And again the broken line outside at a distance R. R is greater than the radius of the shell. So there are 3 different points. One inside P dash, another one at the surface R, and the third one outside the surface at the point P where the electric field intensity is to be calculated. So first thing, we will consider that the positive charge is situated at the surface of the sphere. All the charge is located at the surface of the sphere. The charge that is present here is plus. All the positive charge over the surface, and that is equal to Q. Total charges on the surface of the sphere Q. And we have to calculate out the electric field at different points of the spherical shell. So first one, at external point. Let us consider the distance R. Small r is the distance at which the electric field is to be calculated. So small r is greater than the radius of the shell. We'll draw a Gaussian surface at the point P, which is at a distance R from the center of the sphere O. This point P, we draw a Gaussian surface. It will be a spherical shell. Now we take a small elemental area on this Gaussian surface. Small elemental area on the Gaussian surface, and we will calculate out the electric field, electric flux passing through this Gaussian surface dA. We know that the electric line of forces are normal to the surface. So electric line of forces are normal to the surface at the point P, and the electric field and the area vector is also perpendicular to the surface. As a result, both E and A are in the same direction. So they are parallel to each other. Therefore, the angle between E and A is 0. So, cos 0 is equal to 1. So, we have the flux, the small amount of flux passing through a small area given by the formula d phi E is equal to E dot dA. So, E dA cos 0 is equal to E dA. Now, we have to calculate out the whole flux, total flux passing through the whole Gaussian surface. This was only for a small area dA. We have to find out for. So, we integrate both the sides. Total flux is given by phi E. We do the surface integration E dA. Now, the E is constant. Surface integration of, this is surface integration of dA. dA, pura area, dA is sphere. Sphere is 4 pi r square. Total surface area of the sphere is 4 pi r square. So, total flux passing through the surface 4 pi r square. Mind here, r is the radius of the external spherical Gaussian surface r. So, E into 4 pi r square. Now, from Gauss's theorem, we know that phi is equal to q upon epsilon naught. We compare these two equations. E 4 pi r square q upon epsilon naught. We get electric field is equal to 1 upon 4 pi epsilon naught q upon r square. The flux, we have calculated out the electric field. Electric field at the distance r from the center of the spherical shell is given by the formula 1 upon 4 pi epsilon naught q upon r square. Where r is the distance of a point outside the spherical shell. Okay. This is again the formula. If you could remember, this is a formula of an electric field due to a point charge. So here we can consider if the charge is distributed over a conductor, we can consider that the whole charge of the conductor is situated at the center. It could be considered as a point charge, and the formula comes out to be same. E is equal to 1 upon 4 pi epsilon naught q upon r square. Now, if we have to write this formula in terms of the charge density, we have to write this formula in terms of charge density. The charge density is given by the total charge divided by total surface area. Total charge distributed uniformly over the surface is Q, and the total area, total surface area of the spherical shell is 4 pi r square. So Q is equal to the surface charge density sigma is equal to Q upon 4 pi r square. So total charge Q is equal to 4 pi r square sigma. We substitute the value of Q here, 4 pi r square sigma. 4 pi cancelled out. Electric field is given by the formula surface charge density upon epsilon naught r square upon small r square. Small r is the distance of the external point, and capital R is the distance of the or radius of the spherical shell. Now we will calculate out, this is for the external point. Now we will find out the electric field on the surface of the sphere and inside the surface of the sphere, spherical shell. The electric field outside the surface is given by the formula E equal to sigma upon epsilon naught r square upon r square. Now we find out the electric field at the surface. Now at the surface, small r will be equal to r, and the electric field is given by the formula 1 upon 4 pi epsilon naught q upon r square. If you put the value of r equal to 1 in this formula, r square cancels out. Electric field is equal to sigma upon epsilon naught. It is for the point, it is the electric field at the surface of the spherical shell. The third point, at an internal point inside the shell. So, to find out the electric field inside the shell, such as P dash, the Gaussian surface through P dash does not contain any charge. The Gaussian surface inside the shell does not contain any charge. So, if it has got no charge, there will be no flux passing through the surface. As a result, flux will be equal to 0. We have flux equal to 0. We have E into A equal to 0. And R cannot be 0. These are constant value. Therefore, E has to be 0. So, electric field inside the shell is equal to 0. Okay, wait here. So electric field equal to 0. Now we can simply put this into a graphical representation here. We have a spherical shell from inside of radius r. We have from this electric field inside r. You can find there is no line. Electric field inside is 0. And electric field at this point is E. Okay, electric field at the surface is equal to E, that is given by the formula 1 upon 4 pi epsilon naught Q upon R square. And as the distance increases from the center, then the electric field is inversely proportional to the square of the distance. So there are three conclusions here. At the surface, that is at the radius R, the electric field is equal to 1 upon 4 pi epsilon naught Q upon R square, capital R square. Inside 0, there is complete blank. There is no electric field. The graph starts from this point. Okay, and outside the surface, the electric field is inversely proportional to the square of the distance from the center of the sphere. Okay, so this is how the electric field is calculated. It is an important point. We have completed with the lesson, my dear students. So now you read the lesson and try to solve the numericals.